Okay, so it is our next part for the lecture series, vectors for down, right? Okay, so it is vectors for down, right? Okay, so it is actually our just a continuation from our previous part, I mean part 1 of our lecture series. Okay, so just recalling our part 1, I had just introduced to you some information, some basic information of the vectors, right? So in geometrical representation of vector, you can represent a vector like a straight line and an arrow, right? A straight line and an arrow. Okay, so the length of the straight line actually the magnitude of vector, and the arrow indicates the direction of vector, right? So if it is directed, it is east, so these vectors is directed towards east. Okay, so it was number 1 information about the vectors, and the number 2 was the equal vectors. Equal vectors means 2 or 3 vectors are called equal vectors if their same magnitude of the values and as well as the same directions, right? And the same magnitude, I mean the length of the straight line will be same, and obviously the direction will be same. So these three stuff here represents the equal vectors, right? Because the length of the straight line here, here will be same, and the directions of all vectors is towards east, right? It's very simple. So if you can call it A, so obviously it is an A, it is also A, right? So it is our equal vector set, and the number 3 was opposite vector, right? Opposite vector. So opposite vector means two or just two vectors are opposite vector. That means the length of the vectors will be same. I mean the magnitude of the vectors will be same, but the direction of two vectors are just opposite to each other, right? I mean, if it is directed towards east, then obviously the opposite of this thing, the length will be same, but its direction will be towards west, right? So if it directs towards east, so obviously the opposite of this, here this will be directed towards west, right? But the length will be same. So if you call it A, so obviously this is actually minus A, right? And the last or final information about the vectors is actually a very interesting, a crucial results here. The crucial informations here is a parallel transformation theorem of vectors. I mean the parallel shifting theorems of vector. You can call it parallel transformation theorem. Transformation theorem, or just you can call it parallel shifting theorem, right? I mean if it is a vector, I mean I just introduce an example for my pen here. So if you just transfer this pen parallel to itself without changing the direction. So from here to there, just transfer it parallel to itself. From here to there, from here to there to there. So all of these vectors are equal, right? Because the magnitude of all the vectors, I mean the length of my pen should be equal, right? This length of my pen should be equal, and I just shift it parallel to itself. That means the directions should be equal, right? So if you just call it A, so it is obviously A, is obviously A. So it is an A, it is an A. So actually parallel transformation theorem permits us to transfer the vectors with parallel to itself without changing the direction and the length, right? Okay. So these are all recipes, okay, to digest our vector algebra, right? These are all the recipes. I mean, the representation of vectors here, the equal vectors here, the opposite vectors here, and the parallel transformation, the vital, the crucial theorem here. These are all the recipes which I just digest are the vector algebra, right? Okay. So let me start with the vector algebra. Okay. So just erase some part here. Just erase all the things. Just these actually the previous knowledge or sense. So okay. So let's start with the vector algebra. Okay. Okay. So the vector algebra. Okay. So before I start the vector algebra, I will actually introduce to you some experiment here, right? Some thought experiment, right? Some thought experiment. Okay. So let's start the vector algebra with some thought experiment, right? So just assume a block here. Just assume a block here. Just block placed on your study table. Just the block placed on your study table, and you push the block in that way, right? Just push the block in that way. So all of you know the push or pull is actually a force, right? I mean, if you push or pull something, that means actually applied a force on it, right? We applied a force on it. This push or pull is a force. So if you push the block in that direction, that means we applied a force on it, right? And obviously all of you know from our previous class, the force is actually a vector quantities, right? Just a vector quantities. So just assume you applied a force, I mean you push the block with a force in that direction with 2 Newton, right? Just 2 Newton force. Okay. So our intuition tells us the block will goes in that direction, right? It is just our intuition. Okay, so just our intuition tells us if I push the block in that direction with 2 Newton force, the block will goes in that direction, right? Okay. And if you push the block with somehow 2 Newton force here, 2 Newton force here, so obviously the block will goes in that direction, right? It's very simple. Our intuition tells us if push the block by your hand here, the block will go in that direction, and if you push the block by your right hand, the block will go in that direction. It's very simple. Okay. Okay. So now our first experiment here. Experiment number 1. Here is a block just placed on your study table, and you pushed block by your 2 hands. Okay, you push the block with your 2 hands simultaneously, and you apply just equal force, right? So just such a way you push the block with equal force by your 2 hands simultaneously, right? So block just placed on your study table, and you push this block by your 2 hands in that way with equal amount of forces, right? So if you apply it here, the 2 Newton force, obviously you will apply here the 2 Newton force, okay? And obviously the magnitude of force, the 2 Newton, that means the length of the straight line here and here will be the same, because length of this straight line means the magnitude of vectors, right? So if it is a 2 Newton force, obviously it is a 2 Newton force, and the length of this straight line will be same as this thing, right? Okay. So just think, just imagine if you push the block with a 2 Newton force in such a way simultaneously, then what direction of block will go? Obviously, our intuition tells that the block will go just diagonally, right, in that direction. Obviously, the block will go diagonally in that direction, right? It's very simple. Okay, here is a number 1 thought experiment here. Number 2 thought experiment here is a block here, and if you push the block with your left hand with somehow the larger force, and you push the block with your right hand somehow the smaller force, right? I mean, it is a somehow just as usual is a 10 Newton force. Just push your left hand and somehow assume it is a 2 Newton force. I mean 10, so just breaks it 5 equal parts here. 1, 2, 3. Oh, sorry. I'm sorry here. It's a 1, it's a 2, it's a 3. Oh, sure, it's a 5. So if it is 10 Newton force, if I just breaks it in 5 equal parts, then one of these length is actually 2 newtons. So it is a 2 Newton. Right? Okay. That means you just push with your left hand the 10 Newton force here, and from the right hand it's a 2 Newton force here. Right? Okay. Simultaneously, right? I mean, just a simultaneous force you just apply it on the block with your left hand and right hand here. Okay. And with your left hand you just push a larger force, and from your right hand you just push just a smaller force here. And if I ask you what direction the block goes, obviously your answer will be it doesn't go with the diagonal, but it is inclined somehow here, right? Because inclined with a larger force, right? It will be answer. Just your intuition. The block will go somehow in that directions, right? Okay. This is a number 2 thought experiment, and okay, so just erase it somehow, and our number 3 thought experiment here if the block is here and if you push simultaneously by your two hands, but just like this, but with your right hands you just applied a larger force here. Somehow it is a 10 Newton force. Just cut it 5 equal parts. 1, 2, 3, 4. Oh my god. The 1, the 2, and the 2, 3, 4. Oh, just roughly these are 5 equal parts here. So with your right hand you just push the block with a 10 Newton force, and with the left hand just apply a smaller force like a 2 Newton, right? Because if it is a 10 Newton, so one of these parts actually are 2 Newton, so just length will be the same. Just simple. So you applied the force by your two hands simultaneously here, but with your right hand you push with a larger force, and your left hand you just push block with a smaller force, right? Okay. So what the direction the block goes? Obviously, the block goes somehow in that direction, right? Your intuition, it is obviously your intuition tells that the block will go in that direction, right? Obviously, because it's a larger force here, so the block will somehow incline with a larger force. Just from here, if I introduce a 10 Newton force in the horizontal direction, the block will go somehow in that direction. The inclined with a larger force here. So obviously, it will incline with a larger force here. It's very simple. 3-thought experiment here, right? Okay. Now I just demonstrate this physical thought experiment and observations with a mathematical sense, right? With a mathematical sense, I'll just introduce here. Okay. So our step 1, please represent the block as a dot. Please represent the block as a dot. Okay, these are mathematical sense. I'll just see all of these experiments. I just draw in whiteboard, but this not actually somehow so many experiments here. But I'll draw some mathematical conclusion, right? Okay, so just our first step to introduce these observations into mathematics. Just please represent the block as a dot here, right? So block represents a dot, and here is a 2 Newton force, and here is a 2 Newton force here, right? The same length. This length should be the same. Okay. So just name it is a A, and obviously it will be some another is a B, because the directions will somehow change here. Magnitude will be same, but directions are just somehow is different, right? Okay. So just represents the block with a dot, and our initial configuration here. The 2 Newton force acts on the block, and the 2 Newton force acts on the block. So it is this, right? Okay. Now, our previous class, we'll know the parallel transformation theorem of vectors, right? So just transform these vectors parallel to itself. This A will goes to this, and this B will goes to this. Okay, so it is our old configuration, A and A is the block, and is our new configuration. So the A is the B. Just same thing, because I will just transfer it parallel to itself. The direction is same, the length obviously the same. The length obviously the same. Okay. Just transfer it parallel. So if it is a A, so obviously it is a A and it is a B. It is a B, it is a B. Okay. So it is our new configuration. Okay. So it is our new configuration. Okay. Now, just another transformations I will apply. Just transform this B from here to there, parallel to itself, here to there. So if it is a B, I just shift it parallel to itself without changing the direction. So obviously, if it is a B, it will be a B, right? So it is a B, right? And now place a dot here. Just place a dot here, right? And please connect the initial dot and the final dot with a straight line. Yeah, it is. And just place an arrow in it here. Okay. So it is your actually the direction of block, right? It is actually your direction of block. Okay. Okay. So it is actually the direction of block, right? So just recall what I did here. Initially there was two vectors here and here. These are initial configuration, and I just represent the block as a dot, and I shift this vector parallel to itself from here to there, and obviously from here to there. So it is our new configurations, configuration number 2, these and these, and I just another transformations with the B. So if B transformed from here to there, so obviously it will becomes B, because I just transfer it parallel to itself. And now I placed a dot here to the final case, and I just connect the initial dot with the final dot by a straight line, and I just place an arrow in it. So it is our directions where the block will goes, right? Okay. And just look at this stuff carefully. What you did here, I just push this block simultaneously with the two forces, right? Simultaneously with the two forces. I mean, the block will goes from here to there in that path. Actually, it's a joint effect of two forces, right? It's a joint effect of two forces, because it's a simultaneous action of two forces on that block, right? Simultaneous action. The block will go in that direction by the virtue of two forces, right? By the joint action of two forces. So if one of these forces is A and one of these B, so I can call it is a plus B, right? Just a plus B, because the A plus B means the direction of blocks and the path of the blocks. It is a joint effect of two forces, right? The joint effect of two forces. Okay, so this is actually A plus B, I mean the addition of two vectors, right? Okay, so similarly for this thing, just the same procedure I will follow. Just represents the dot, sorry, the block as a dot. This is the initial configuration, and it is a 10 Newton force here. So 10 Newton force here, and it is a 2 Newton force here. Just name it A, just name it B here, and it is an initial configuration, and just transfer this A parallel to itself in that direction. So these are new A actually, right? And if you shift this B parallel to itself from here to there, it is a new B. and obviously just transfer this B from here to there. Okay, and just place a dot of our final configuration here and just connect these two dots with a straight line. Yeah, and just place an arrow. Okay, so it is a direction, right? The block will goes with a joint impact of two forces. The block will goes in that directions, right? So similarly, it is a joint impact of two forces because I just applied the two forces here simultaneously, and the block will goes with a joint impact of two forces. So obviously it is a B, right? So obviously is A is a B, so obviously it is a A plus B, right? Addition of two vectors, right? Okay, and just similar thing here. Just okay, so just simple. Just block represents a dot here, and here 10 Newton force is the initial configuration. Just name it A, and the 2 Newton force. Just name it B, and just shift this A from here to there. Just a parallel shifting. Is a new configuration, a new A, and these are new B. Just shift parallel to this vector from here to there. These are new B, and just shift this vector from here to there, and just place dot here, and just connect these two dots with a straight line, right? Okay, so it is actually, and just place an arrow here. Okay, so it is our directions of block, right? Because the joint impact of two forces on the block, and the block will goes in that direction. Obviously, if I applied two forces here, the block will goes in that direction and inclined the larger force. So the joint impact of two forces. So B is actually, you can write it A plus B. Right? Okay. So it is our addition theorem of vectors. Right. Okay. So it is our addition theorem, and probably all of you think that it is true for the perpendicular set of vectors. I mean, just I draw all the vectors in a perpendicular, right? Here just it is and it is a perpendicular. Here it is and it is a perpendicular. It is and it is a perpendicular. And obviously, all of you think just this rule actually valid for the perpendicular set of vectors. Yes, it is no. It is not true. It is valid for all types of vectors. I mean, not just a perpendicular set of vectors. I mean, if you draw this addition theorem with two vectors, something like that. I mean, if you just draw this vector here and here, and it is a dot here, just it is a A, it is a B, and it is a block, right? It just represents the block dot, right? So just transfer the A from here to there. Is a new configuration with A. Just transfer B from here to here. Okay. So it is our B. Just a parallel shifts. It is a A. It's a B. And our natural sense, and our previous situation, just transfer B from here to there, parallel to itself. Okay, so it is our new B, and just place a dot and just connect the initial dot with final dot and place an arrow. So it is our A plus B, right? Okay. Just it is not true for the perpendicular set of vectors. It is valid The addition algebra, the addition rule of vectors is valid for all the set of vectors with all angles, right? So the angles is not 90 degree, right? Yeah, the angles of A and B is not 90 degree. It's somehow the less than 90 degree. Okay, so it is our addition rule for the vector algebra, right? Okay, and then the next class I will introduce to you the subtraction rule of vectors, the multiplication of vectors, right? And then I will introduce to you the algebraic representation of vectors, right? Okay.